So the plan for today is basically to implement some infrastructure to help with automated parser testing to check the structure of the AST. Right now, if I run this, we're basically just printing stuff in JSON to check that it works properly. But this is pretty difficult to test against because it's a lot to type. JSON isn't necessarily ordered either. So instead, I want to implement a printer that will print an AST as an S expression. So I was thinking of having this function sprint, which just for now takes a node and returns a string. And this will just be a type switch on the node. So for each case of AST node that we have, we'll basically just tell it how to print this as an S expression. So in the case of any of these pointers, we'll return some string. And in the default case, we'll just panic because we want the printer to be able to print anything. So if we hit the default case, we should panic so we can just implement it. So we'll just say sprintf unhandled type, and we'll just put in the type here for the node. So for binary nodes, we just need to get the string for the LHS, which will just be another call to sprint. Same for RHS, and we'll basically just return an S expression, which is the parentheses, followed by so we'll do the operator first. So we'll do node.op.string. That will be followed by the LHS, and then that will be followed by the RHS. Unary prefix is pretty similar, but the prefix only has an RHS, so we can get rid of the LHS. And then postfix is basically the same, except this one is it only has an LHS, and so actually we need to print dot LHS, dot RHS, and RHS for this one, and LHS for this one. Ident is pretty easy. We can just return the node name. And then integer, I actually want to change the way that integer is represented in the AST. I don't really want to be parsing out the integer in the parser. So I don't want to be creating an actual int at this point. There's no point in having the actual int in the AST because it's not going to be needed until we generate sort of like this linear assembly-like intermediate representation. So I actually want to take this out, and instead the integer is just going to be described by the start and end offsets that are in the token. So we'll take the start and end from the token. So this will be start is p.next.start. And the same for end. And then we don't actually need to do any parsing or error handling there. That will be done later on after type checking. So in AST, we can change the int to just have a start int 32 and an end int 32. And so the printer we'll need to accept the file. So we'll need to say file lexeme node.start and node.end. So we'll take the file in as a second parameter. Token, this one should be this package. So if we go back to main and try to start printing some things, and we'll see what we've missed. So we'll do fimp.println, ast.print or sprint, and pass in the node and the file. Not enough arguments to sprint. Okay, so in the print where I recursively call, I need to pass through the file again. So this prints 1 plus 2 plus 3 plus 4. So if I do something a little bit more complex, so let's say minus ABC or negative ABC plus 123 multiplied by 999. Okay, so this gives us 123 multiplied by 999, and that's the addition of that result and the result of the negation of ABC. So that's working correctly. So the idea is that basically in the language, I want to have comments where I'll start a comment with some word like want, and then I'll write the S expression for what I would expect from the tree that is connected to that comment. So this entire tree would be connected to the comment above it, and then I can print this tree as an S expression, and I can extract the thing that I want from the comment, and then I can just compare them and test that way to see if the AST is being built correctly. So in this case, it will be that I want the multiplication of 1, 2, 3, and 999, and then that should be the addition of that result along with the negation of ABC. So I want to be able to extract this comment as well. So to extract the comments, I'll need to add them to the scanner. And I don't really want the parser to have to deal with comments, so I'm actually going to discard them. And so they won't go into the file.tokens slice, which means that there's no point in trying to add a test here, because this is looking over the file.tokens slice. I could add other tests, but I think I'm going to leave them out the tests, because if they aren't being scanned properly, and they aren't being attached to other trees that are generated by the parser, then the parser tests will all fail, and we'll know that it's not working anyway. So the file, I'm going to call any comments or anything that's any token that's not important to the parser, I'm going to call trivia, because I've seen that word used somewhere else. It might have been related to the C# compiler, but I'm going to call it trivia. So we're going to have trivia tokens that we save up here, and then and so what the scanner is going to do is it's going to fill up this trivia token slice. So when it sees things like comments, it will put them in the trivia token slice and not the tokens slice. So it's like it's discarding them for the parser. But we should be able to take some file offset and look up the trivia tokens that are associated with that offset in the file. So we'll just start by creating the comment tokens and building them up in here and sort of discarding them for the parser. So if I run this at the moment, it should fail because comments don't exist. So this is treating it as a prefix function in the parser, and it doesn't know how to deal with it. So it's trying to look up a prefix function, and then it's trying to call the function on nil. So I need to go to the scanner, or actually I need to go to the tokens and add a new comments kind. And then in the scanner I need to generate comments. So we'll just say that, for example, if the byte that we've just read is a slash, and the next byte is a slash, then that counts as a comment. So we'll read while we're not at a new line, and then we'll set the kind to token.comment. So I need this new not new line. So not new line we'll define it the same sort of way as whitespace. We'll just say it's not is new line. So is newline will just be the return of b equals n. Okay, and now when I consume this token, I can basically look at the next at the token kind and say that if it's a comment, then I'll add it to the file dot. So this will be s.file dot trivia tokens. I'll just append it to that slice. And in any other case, we'll append it to the normal token slice. And then if it was a comment, we'll continue. Oh, we don't need to continue. That's fine. Okay, so now this works is basically throwing away the comment for the parser. So the parser doesn't even need to look at the comment anymore. So what I'd like to be able to do is if I go to main here, let's say that we loop over all of the tokens in the file that we've scanned. So we'll say range over file.tokens. And for each token, I want to look at the start offset of the token in the original source and query any comments that came before that. So any leading trivia that comes before it. So this unary negation here, this one, when I query its offset, should be attached to these two comments. So I should get back a slice of trivia tokens that map to those two comments. So we'll say, for example, we'll query it by saying file.trivia, and we'll pass in the tokens start offset. And this will give me back some trivia struct where I can just, say for token in the range of trivia.leading. We'll do format.println on the file.lexeme for token.start, token.end. So this will give me the lexeme of the comment token that is attached to that starting token offset. And that would give me all of the trivia that I can then look at the comments and extract the test cases for. So file needs to be able to query these things. We'll say func f file trivia, and we'll take an offset and we'll return some trivia struct. So I'll create a trivia struct up here. This will have leading, which will be some slice of tokens. And what I want to do is look up the offset that maps into some range in the slice. So I need to be able to say, let's say var trivia will be a struct that will return. And we'll say that if leading OK for f dot leading trivia at the key offset. So leading trivial, and if it was okay, we'll do trivia.leading equals f dot trivia tokens from leading.starts to leading.end. So basically leading trivia will be like a map that maps an offset to a slice index into trivia tokens. Or this will be, the offset will map to a range. So we'll have leading.start and leading.end. So we're going to need this trivia range here as well. And we'll have leading trivia, which will be a map of int32 to trivia range. And then we'll just make that map here for now. So we'll say map int32 to trivia range. So that way I can basically look up a trivia range based on an offset, and then I can use that trivia range to get the subslice of the trivia tokens for this trivia struct here. So the scanner, right now, undefined leading trivia on file. Oh, this needs to go to this is a map to trivia range. Okay, so right now this doesn't print anything because I haven't put anything in the maps or I am populating trivia tokens, but I haven't mapped anything in leading trivia. So in the scanner, I need to keep track of where some trivia starts and where it ends. And when I hit a token that's not trivia, I need to map that token's offset to the range that I've been keeping track of. So we'll have some start trivia index that can be int32. And when we start scanning, we'll set that to -1. So -1 will be the sentinel to say that we haven't actually started tracking any trivia yet. So what I can say is that if s.trivia start trivia index is less than 0, then I'll set it to whatever the length of f.file.trivia tokens is before I append to it. So this will be the start index of the one that I'm just appending. Then when we hit a token that's not trivia, we'll basically say that if we have a start trivia index, then it means we've started tracking some trivia tokens. And in that case, we want to set s.file.leading trivia. So we want to map the token's position. So this non-trivia token's start position in the source should map to some token trivia range, where the start is the start trivia index and the end is the length of s.file.trivia tokens, I think. Then after that, we've assigned this range to that offset, so we need to set this back to -1. So this is line 104. This should be s.file. Okay, so we're looping through all of the tokens, and for each token we're printing out any leading trivia that we find. So maybe I should also, just to check that it's actually working properly, maybe I should also be printing out, let's say we'll print out this with a few, like an arrow before it, and we'll print out the lexeme of the token. So we'll change this one to trivia. And we'll print out the lexeme of the token that it's associated with. Okay, so in this case, we've got leading trivia for the minus token, and the first one is 1, and the second one is this. So I'm actually printing this twice because I've done it here. So for the unary minus, we've got 2 pieces of trivia, and for all of the other tokens, we have nothing. But we'll also need inline comments, just because we're dealing with comments right now. It would be useful to see the inline comments or to query them. So for example, if I put inline here, right now that inline is being associated with the next token, which is the plus. oh, sorry, which is ABC. So this is being attached to this one, but really I want this to be attached to the unary minus because it's on the same line. So I think to do that, we'll basically just have another map. So we'll say that inline trivia is going to be a map from an offset to just a single index, because an inline comment will just be one token in the trivia tokens slice. So that means that I could say, for example, if inline for inline trivia, if we find an index for that offset, then we'll say that trivia inline is a pointer to the trivia token at inline. So I need to just make this map as well. And trivia needs inline, so this would be a pointer to a token. Okay, so now the scanner just needs a way to attach an inline comment to the previous token when it hits a new line. So when it hits a new line, we need to say that if we've got a start trivia index and we've got a previous, and we've got like a last non-trivia token, then we should map that last non-trivia token to the index of the comment. So we need to keep track of the last trivia token start position so we can use it later on. So we'll call this last non-trivia position. I think for the same for this, we'll set this to -1 so that we know if we've actually got it or not. So if there's anything that's non-trivia here, we set that to the start position of the token. If there's any comments, then this still works just fine. But now I need to know if there's a new line, so I think the easiest way will be to just do that as a new line comment, a new line token. So we'll say that if we hit some token that's new line, then we'll say that if the last non-trivia position is greater than or equal to 0, and we have some start trivia, then in that case, we will set a mapping from inline trivia to last non-trivia position to the start trivia index. And then in this case, we need to now say that the last non-trivia is equal to -1, so we'll restart that, and we'll restart this one as well. We'll see how this one works out. So we need a new scanner, and yeah, we also want to make sure that we don't include these in the parser token slice either, so that's fine, we don't need to add those to tokens. And they're not trivia either, so we're completely discarding newline, so that's fine. So in token, we need a new line kind. So we've got newline, newline, and newline. And then in the scanner, we actually need to emit some newline tokens instead. So is newline, which we've already got a predicate for. So if it's newline, we'll just read a single bytes, and we'll just return token.newline at the start and s.pos. And then that means that we don't want to skip new lines because they should now be tokens, so we'll take them out of this white space. So now ABC doesn't have a comment associated with it, but we want to see if this one has it. So if we go to main.go and we'll have a look at this, we'll put like a plus or something at the end for an inline one. So we'll say if trivia.inline is not equal to nil, then we'll try and print the lexeme for that inline trivia. So now the inline comment is associated with the offset for the unary minus. So now I need a way to collect all of the leading trivia, remove any prefixes and spaces and stuff, and join it all together. So I need to walk the AST. So it might be useful actually to have a walk helper here, where we'll take a node and then we'll just do a pre-walk at the moment. So depth first, pre-order, and this will just be a function that takes in a node. We won't allow any returning of errors or stopping early or anything like that. We'll just walk the whole thing. So in this case, we've got a switch. In fact, this is basically going to be the same as the print switch case at the moment. And all we'll do is, in the case of binary, we'll walk down the node with the pre-function passed in. So this will be LHS first, then RHS. Then after we've done that, we exit out. That's fine. Before we start, we'll just say if node is nil, then we'll return. Then we want to say that if pre is not equal to nil, we'll call it on whatever node we've got. So now this switch case down here, this type switch, is basically just responsible for walking the tree. So in unary prefix we've got an RHS, in this one we've got an LHS. And in ident and int, we don't actually need to do anything. So these are leaf nodes, so we'll do nothing. So now in main, we'll just try walking. We'll just say walk node. We'll take in some node, which is ast.node, and then we will just maybe to start with, we'll just try printing to start with, we'll just try this. We'll just do this on every node and see what comes out. So we'll comment this out. Okay. So we're printing the whole tree first, then we're going down into the left-hand side of that first binary, which is this negative ABC. Then it goes into the RHS for the unary, which is ABC. So it looks like it's doing it in the right order, and it's visiting all of the nodes. So within here, we can basically try and get the... So instead of going over all of the tokens, we'll basically need like a start for a node. So I think we'll have to implement some common function on all of the nodes called span, which will return the start position and the end position of that node in the source file. So if we go to AST, we'll change node from any to an interface, and this will be span. So this will return two offsets, the start and end. So let's go down to int first. So we'll say int has span of So this can just return the 2 positions it got from the token, so this one's easy. And end, okay, and then we'll do ident. So ident, we need to actually keep a start offset at least. And then for the end one, we can basically just do the length of the name plus the end. Oh, plus the start. So start plus the length of the name lexeme. For unary postfix, I think we'll need a start offset for this one as well. So this will be int 32. So this will take u.start, and then we'll have end here, which will be the result from calling u.lhs.span. So prefix is going to be similar, but this is going to use the start instead. So this will be start, and then the end will be u.end. And then binary is just going to be basically a call to LHS span for the start, and then RHS span for the end. So this one's binary, this one should be prefix. So if we go back to main, so we get the start of the node. And then we can have a look at, we don't need to loop over tokens anymore. We'll get the lexeme for start and end in the original source so that we can see what we're actually inspecting here. So we'll do start and end for the lexeme, for the whole lexeme of the node. And then we'll take the trivia based on start. Unary prefix needs to change a bit. So this one has an RHS. So now we get so we've got start node. Let's also print the type. So I think if we print the type, the lexeme, and then hopefully that'll make it a bit more obvious. Okay, so for binary, we've somehow got the comments in here. So this is correct for the binary node. We want the lexeme from the unary minus to 999 here. Let's remove this inline comment. Oh, okay, I know what's going on here. In the parser, I am not assigning the new fields yet. So basically ident, this needs a start, which will be start, we'll just say that start equals p.next.start. Unary postfix needs an end. Oh no, this needs a start as well. So we've got starts for the unary postfix. Unary prefix needs an end, so this one will be the token end. And now we get the correct lexeme. So this entire lexeme here for binary is going on the, so we've got unary prefix. The unary prefix is missing though, so unary prefix has no, I've got these the wrong way around. So start is for the unary prefix, we want start because the op is before. This one should be start. This one should be end because the op is after. So if we go to AST, we'll just switch these ones around. So this one should go down here, and this one should go up here. But this one should take RHS, and this one LHS. So now we get binary as the entire expression like we'd expect, and it's got these leading comments attached. Unary prefix also has the same leading comments because the unary negative here is the same offset in both trees. So we'll have to keep a map of what we've already seen. So we'll say seen is int32 struct. And we'll just say that if we've seen start, then we'll just return and not do anything. Otherwise, we'll set the value of it. We want to make map. Okay, so now we only get it once, and because it's a pre-order traversal, we're seeing the binary comments and not the unary ones. Yeah. So because we've already seen the start offset for the binary, the unary one doesn't even print. In this case, there's no point because we're only using it to collect together comments that would be used for test cases anyway. So in here then, I think what we can do is basically each loop of this where we find the trivia would become a test case. So we don't care about the inline, although I should test the inline quickly. Okay, so this one seems to be seems to be printing the lexeme inline. That's fine because that's the original source representation. And it's being associated with these two leading tokens and this one inline token. So if I do another comment here, this one should be associated with the ABC, which it is. So if we get rid of these comments, so what I want to be able to do is, for example, split this onto a new line to format the S expressions for tests, like this. So I want to be able to discard the want and join the rest of them together. So we don't care about the inline in this case. What we do want to do though is just loop over all of the lexemes. So we've got a lexeme here, this is the line. Then we will basically check the line to see if it begins with something like want. And we'll keep a slice of lines that should become the test case. So we'll call this, yeah, we'll just call this lines. And then we'll just say that we'll just keep track of whether we've seen the prefix that we want or not. We'll say is test case. So we'll say if the strings dot has prefix. We'll say if it's got the prefix want like this, then is test case is true. And if is test case is true, then we'll basically push this onto the lines. So we'll clean it up and we'll push it onto the lines. So line will be strings dot trim prefix. So we'll remove the want prefix first, then we'll remove any just normal prefixes for comments if they exist. And then we'll also trim space as well. And we'll append that to lines. So if the length of lines is greater than 0, then we'll basically want to get our test case straight. So we want to say want is the print of the actual node, and what we got is the strings.join of lines with a space. So we'll just print each of these. So we'll print want is want and got is got. Declared and not used end. Yes, so I'll get rid of that one. Okay, so want and got, they are coming out as the same string, except this one's got an extra space on it. I think I need to only do this if line is not empty string. Okay, so because they're both the same, this will be a test case that would pass. So I think maybe what I'll do is we'll say that this is a test case. We'll try and put this into the parser and just do a simple test case. So let's just comment this out. And we'll go into the parser. So we'll say parser test. So this is testing.t. The test table will just be a slice of strings. So these will be files of fin code. So we'll say, for example, expressions .fin. And then we'll say for each test case in the test table, what we'll do is get the bytes for, so we'll read a file and we'll say that this is test data / test case. So we'll have, for example, test data as a folder in here. We'll have expressions.fin, and then we'll have 1 + 2 multiplied by 3, for example, which would have the comment want multiply 2 and 3 with the addition of 1 and the result of that. So we'll read that in. We'll want to use this code to do the walk. So we're basically going to need a scanner. We'll need a parser. If there was an error reading the file, we'll just say that that's a fatal error. And then what we want to do is just say create a new file. So we'll say file is token.newFile. This will be made from the file contents. Then we'll run s.scan on the file, and we'll have node equals p.parse on the file. And then the test cases can just run in here. So we'll say if once does not equal got, then t.error f want something. So I think I want to format this a bit better. So we'll do a newline want, and then we'll say newline tab. So we want this string. Then we'll do newline got, newline tab, and then we'll put the got. I think that might be readable enough. Okay, let's just see what I've missed. So we'll try and test. Want lexeme this got this. Okay, well, I'll deal with that in a minute. Not enough arguments to new file. Okay, that's fine. So the new file is the test case name. System cannot find the file specified. Test data expressions.fin. Yeah, okay, expressions.fin. Okay, that actually passed. I think I'll have to make a mistake in here, so we'll say divided by 4. Expressions.fin divided by 4. Okay, so we see we want this, but we got this. So I've actually got these mixed up. The got is what we got from the AST, from the actual AST, and what we want is what we've joined together from the comments. So we're saying that we want this, but we actually got this from the AST. So if I remove that divided by 4, it now passes, so I can actually test the parser now, automated testing. So let's deal with this final test failure. So we want lexeme this, but we got this with a new line on the end. That's because the scanner, when we create an unknown token, is going until the end of white space. So I think what we actually want to do is read while I think we need two different things here. So instead of is white space, we'll say is insignificant white space. Insignificant white space. Or we'll say is skippable white space. That's a bit more descriptive as to what it actually is. So we'll say this white space is skippable, and not white space is anything that is not skippable white space, and it's not a new line. Okay, that passes again. Okay, that's it. So I think I'll leave it there for today. And next time, now that I've got this infrastructure in place to do some automated parser testing, I'll basically just start parsing out more of the language.